Okay, lesson 431. So, in this chapter, you've analyzed polynomial functions, rational functions, right? So today we're going to see how these types of functions can help us solve polynomial and rational inequalities. So far in this course, we've used inequality notation to describe intervals. Another way of describing intervals is to use interval notation. So review the examples below and discuss with your team. So complete parts A through F. As you work through the rest of the lesson, write your answers using interval notation. Note that U means a union, right? So it's a union of the two. So if you look here at the examples they give us, so they give us inequality notation. So x is greater than -7, and then they give us interval notation. Well, the interval is the interval in which they're talking about here. Well, greater than -7 means from -7 to infinity, right? For as far as it goes. So then if you look at the next one, we have x is less than or equal to 21. So again, that interval less than 21 is -infinity to 21. Now, notice there's a bracket on the 21. Okay, that just means equal to. So the equal to line there and the bracket, that's how you signify that. So if we look at the next one, -7 is less than x is less than or equal to 21. So that interval is in between -7 and 21. So you can see there the interval notation is -7 to 21. And again, 21 has the equal to, or the bracket. Okay, and then here the or, right? So x is less than -7 or x is greater than 21. So we have two different intervals here. So we have -infinity to 7 and then 21 to infinity. And that's where we have to use that union of the two. So again, so let's do A through E here. So A, express x is greater than 35 in interval notation. So greater than 35 is going to be A is going to be 35 to infinity, right? So infinity always has a parentheses because you can't touch it, right? You can't reach it, you can't equal to it, right? And then 35 is equal to, so it has a bracket. B, express -3 to 18 in inequality notation. So -3 is less than or equal to, it has a bracket, x, which is less than 18. We're talking about in between -3 and 18. And then C, we have 14 less than or equal to x less than or equal to 52. So again, 14 to 52 is our interval. 52 is not equal to, 14 is. So we have a bracket on 14. Okay, express -infinity to 6 in a union of 97 to infinity. So x is going to be less than 6, right? No equal to, or x is going to be greater than or equal to 97. Okay, and then express x cannot equal 0 in interval notation. So x has to go from -infinity to 0. And then that's a union, right? Or 0 to infinity. Okay, so here's the thing. A lot of times in these lessons, we've been talking about the domain. And as the domain, we may put x cannot be 0, which is way simpler to write in inequality notation than it is to write in this interval notation. So most of the time, you'll see me use interval notation because like writing this is a lot easier. But when it comes to like x cannot equal, you'll see me go back to inequality form for that case. Okay, let's look at the next one here, 103. A portion of the road meanders through the countryside can be modeled by the equation. So we have this equation where -5 is less than x is less than 5, and this is kind of our bounds, and then x equals 0 divides the north and the south. So work with your team to determine which sections of the road are in the north and in the south. Use multiple representations to justify. One of these should be algebraic. So first one, let's just graph it. That's going to be the easiest one. So let's just graph this. So 0.03, parentheses, x cubed. And then it was minus 4x squared minus 11x plus 30. Okay, and so if we look here that x is greater than negative 5, and then x is greater than or less than 5, that's our bounds, right? And then we had that y equals 0 divides north and south. So what are we talking about here? The north is from negative 3 to 2. So I'm going to write that over here. So north, let's go North County is from negative 3 to 2. And then South County is going to be from negative 5 to negative 3. Right? Negative 5 to negative 3 is in the south. And then from 2 to 5 is also in the south. So from 2 to 5 is also in the south. All right, so now let's look at like doing that. So they said do that algebraically. So basically we're just finding the zeros there. So, instead of y equals, right, we're going to set that equal to 0. And we're going to solve it the way we've been solving these all chapter. So what we will need to do, since we can't factor this, we will have to go to our rational roots theorem. So we'll set it equal to 0. The 0.3, if we divide that over, 0 divided by 0.3 is still going to be 0. So that 0.3 technically goes away. 0.03, sorry. And then it's rational roots theorem, right? So we're going to take factors of this divided by factors of 1. So factors of 30 are 1 and 30, 2 and 15, 3 and 10, and 5 and 6. So what did I leave out? 10, 15, 30, all divided by 1. Well, we already know these zeros, luckily, so we're going to go ahead and kind of cheat a little bit. We're going to use the easy way. So let's just use 2 maybe as our first one. So we'll use 2 and divide this out. So 1, negative 4, negative 11, and 30. Bring down the 1. 1 times 2 is 2. Negative 2. 2 times negative 2 is negative 4. Negative 15 times 2 is negative 30. No remainder. Okay, so we know x equals 2 is one of our zeros. Right, and then the other one here, we're going to have x squared minus 2x minus 15. Well, we can factor this. So factors of 15 that subtract to 2 is going to be 5 and 3. So negative 5 and a positive 3. Again, we set these equal to 0. And we get x equals 5 and x equals negative 3. So we get our 3 zeros there by doing that algebraically. So, okay, so 104. The next stretch of road can be modeled by the equation. So we have this equation, okay, between 5 and 30. To determine the sections of road in North County, solve the inequality graphically. So let's try to graph this. So there's 4 zeros and a 5, and then there's parentheses x minus 5, parentheses x minus 15, and then x minus 22 squared, and then I think x minus 30 is the last one. Is that right? Yep. And so they want to know where it's, where this is greater than 0. Okay, so if we're looking at this, right, we're looking at where is it greater than 0. Okay, so let's look at these zeros, right? So we got a 0 at 5. Right, and it goes all the way to 15. So 5 to 15 is going to be greater than 0. 15 to 22 is less, looks like. Okay, but it's also less all the way to 30. So really 5 to 15 is our only greater than. okay? So work with this to solve it algebraically. So algebraically, we see our zeros. This is in factored form. We have 5, 15, 22, and 30. 22 being a double root, right? So how could we determine, right? Well, this is what they're working on here, okay, is looking around those zero values and figuring out where the graph is around those values. Since we know those are zeros, we can basically, and I'm going to kind of clean this up and shorten this a little bit. Since we know our zeros, we know they're at 5, 15, 22, and 30. We can then plug in points around those values. So I'm going to say 0, 6, 20, 25, right? And I'm going to plug those in and then see where they are. So if I took 0 and plugged it in everywhere there's an X, what kind of number am I going to get? Well, I'm going to get a negative number, right? The zero value's down here, right? So if I plug that into my calculator, I'm going to get a negative value. So that means it's going to be negative down here. Okay, for 6, I'm going to get a positive value. Okay, and I don't have a calculator to show you, but again, you're just plugging this back into the original equation. For 20, I'm going to get a negative value, right? And then for 25, I'm going to get a negative value. Finally, after 30, I will get positive value. So I can see right now where this is above the x-axis and then where it's below the x-axis. And so that helps me determine if it's greater than 0. Okay? So pretty cool here. Now, so the same deal here is on this next one. You know, you can also do this to see where it's less than 6. Same deal. But the best way to do this is going to be subtract the 6 over, set it equal to 0, and then do it that way. And then so for the rest of these, the best thing to do here is to graph these out. And so you can use Desmos, you can use your graphing calculator to do this. And then there's a way that you can actually put inequalities into your calculator to then show where your set of solutions are. Because here's the thing, when you're solving for inequalities, your solutions are going to be a set of solutions, not just one. So let's look at A here in Desmos. We'll do the best we can of graphing this. So we have x minus 1 divided by x squared plus 5x minus 36 plus 5x minus 36. Okay, and then we have that it is greater than 0. So you can see here, it changes this graph a little bit, right? So we can see that there's shaded regions, okay? And we can see what this looks like as far as the shaded regions go. Okay, so we still have our isotopes here, okay? We still have, well, Coach, what would this look like, without that, right? So we have this deal here. We have a hole, right? And then we have our vertical asymptote, right? So, sorry, we have 2 vertical isotopes. If I can get to them, yes, there we go. Okay, so we have 2 vertical isotopes there, and then, we have, when is this greater than 0? Okay, well, we have to test those. We have to test those points, right? So we can use, these techniques up here to test our values, to test when these points work. And that's how we find, like, what part of the inequality or what values work for this and what values do not work for this. So it's using this testing theory to test these. And so, where are our critical values, right? Well, it's where these zeros or so number 1, right? Like, you have to consider the 0, right, which is at 1. Right, so where this x minus 1 equals 0, because this one's not equal to, it's greater than. So x equals 1 is a critical test point, and then our asymptotes, which is going to be -9, and at 4, right? So those are our critical values, right? And then we would test points around these values just like we did here to see now, are those values going to get us greater than 0? And that's what we're looking for in our solution set. So that's what you do there. Again, critical values, looking for those values that are going to get you those things, and then your asymptotes, holes, and then you're testing those to see, again, where your solutions would be, within what interval are the solutions in. So hopefully this helps. If you need me to come work some of these out more, I can definitely do that to help you out.